Bismillahirrahmanirrahim. In this lecture, you will learn about the ideal gas law. And previously, we have already studied the three individual laws, which one is the Boyle's law, Charles law, and the Avogadro law. And very simply, the ideal gas law is the combination of these three different gas laws. And briefly, I'm going to explain over here. In the Boyle's law, we have already discussed that the volume is inversely proportional to the pressure. And when you remove this proportionality sign, you will have a constant on the right hand side. This is represented by the small k, and this the volume would be k over p because it is one over here, or you can simply say what would be the value of the k, that would be equal to v multiplied by the p, and this is given over here. And important thing is uh, here is this Boyle's law is going to be implemented at constant number of moles of the gas and its temperature. So these two variables will remain constant, and then you will find the relationship between the pressure and the volume inversely proportional to each other. And in the Charles law, we have discussed that the volume is directly proportional to the temperature. And say in same way, when you remove this proportionality sign, you will have the constant on the right hand side. This constant may be called as the Charles constant. And when you have you have to find the value of the k would be v divided by t, and this is written over here. Again, important thing is this Charles law is at constant number of moles of the gas and constant pressure. So in all of the cases, you have a relationship between two variables, and you have to maintain the two other variables constant. In the Avogadro law, the volume is directly proportional to the number of moles, and when you remove this proportionality sign, you will have the constant on the right hand side, and you can get the value of the constant. The constant that would be the v divided by n, and this is the over here. This is called the Avogadro law constant. So simply what we have studied over here in detail, I have already explained in the individual slides in the previous videos. And here you can say that the volume is in three of the cases, volume is inversely proportional to the pressure, volume is directly proportional to the temperature, and volume is directly proportional to the number of n, or the number of moles of the gas. So you can write in this form over here. That means volume is that inversely proportional to the pressure in case of the Boyle's law. Volume is directly proportional to the temperature in case of the Charles law, and volume is directly proportional to the number of moles in case of the Avogadro law. So actually you are joining all these laws together, and again there is a proportionality sign over here. When you remove this proportionality sign, now you have the constant on the right hand side, and this constant is called the gas constant. And when you rearrange this equation, P is in the denominator over here. This is going to multiply with the V, and this equation will become PV is equal to nRT. So this is just the rearrangement of these variable. I have put n before, then gas constant, and then it is the temperature. So here this constant we know that is called the gas constant. And this equation is called the ideal gas equation. Now again, in a similar way, you can prove that the gas is the ideal by using ideal gas law. And if it is going to follow this equation, that means the gas is ideal, otherwise it would be non-ideal equation or non-ideal gas. So the next is, by using the ideal gas law, you can also derive, or you can also explain the three laws which we have explained before this derivation. And as you know, this is the equation PV is equal to nRT. And for the Boyle's law, here the number of moles and the temperature are the constant. because there is a relationship between the pressure and the volume. So if you put the N and T are the constant, and of course this is the gas constant, this is also will remain the constant, and by using the same equation, so PV is equal to nRT, and PV relationship between the pressure and the volume is called the Boyle's law, and all these are the constant, and this will be equal to the small k. So now you know that how can you calculate the value of the small k. Small k is equal to nRT. N is the number of moles of the gas, R is the gas constant, T is the temperature. You know all these three, you can get the value of the k, which was previously unknown. So in a similar way, you can also derive the information of the Charles law out of this gas law. And you remember that the Charles law is when N and P are the constant, number of moles and the pressure is constant, then it is the relationship between the volume and the temperature that is called the Charles law. So I am just rearranging this equation because this in the Charles law, I am just keeping on the right hand side the variables which are going to be followed by each law individually, and on the right hand side the constant, because we have already derived this equation before. And now here I am going to calculate the value of the k actually in each of the case or in each of the gas law. So in the Charles law, there is a relationship between the volume and the temperature. So you just rearrange this equation, moving temperature to the left hand side and pressure to the right hand side, and this equation will become like this. And again, this is the N, R, and P are the constant, and this constant is equal to the small k. And here this Charles law constant you can calculate by using the number of moles, gas constant, and the pressure. In a similar way, you can also define the Avogadro law. Avogadro law is the relationship between the volume and the number of moles. Again, rearranging this equation, keeping keep moving the number of moles to the left hand side and the pressure to the right hand side, and this way equation will become like this. And Avogadro law is followed at constant temperature and the pressure. So Tp are the constant, R is of course is the constant, which is called the gas constant, and this whole three constant will give another constant that is called the K. And here you can calculate the K by using all these three constant. So which was the constant which was unknown before. Now by using the ideal gas equation or the ideal gas law, you can calculate the K in all of three laws. So this is all about the ideal gas law. Now you can calculate the value of the gas constant by using the same equation, and this is very simple. We are going to use the this one equation, PV is equal to nRT. So R will be equal to PV divided by N and T. So we are using this equation. So R will be equal to PV divided by NT. So this can be calculated as standard temperature and the pressure, and these are the condition for the standard temperature and pressure for the gases. It is temperature as 0 degrees centigrade, or you can call it 273 Kelvin. Pressure is 1 atmosphere, and now put the value of these standard in this formula, and this is the pressure. Pressure is 1 atmosphere. When pressure is 1 atmosphere, the gas of having 1 mole of the gas, 1 mole is having the volume that is equal to 22.414 liter. So this is also the standard, the volume of a gas at the standard conditions. So 1 atmosphere 22.414 liter, and this is 1 mole, and temperature is 273.15 because it is 0 degrees centigrade. So you have to convert the 0 degree centigrade to the Kelvin. You have to add 273 in it, it will be 273.15. So if you do not use the fraction, it is also okay. You can just put the value of 273 Kelvin over here. When you solve this one, this will give you the value of 0.082058, and the unit of this one as written over here, this is the atmosphere liter, per mole per Kelvin. So this is just the rearrangement. This is as atmosphere liter, and this is just being rearranged. Kelvin is first and the mole is second because this is the international representation of the unit of the gas constant. Otherwise, there is, if you want to put the mole first, then Kelvin, it is also okay. So, but here the more appropriate to use this one, liter atmosphere per Kelvin per mole. So this is the unit of the gas constant in this one values, but here there is another value is given 8.314 joule per Kelvin per mole. This is the value in the SI units. So and this is also given over here when you use the pressure in Pascal and the volume in the cubic meter, then it will rearranging the units. This will give you the value of 8.314 joule per Kelvin per mole. And what important over here is, one is the importance of this calculation. How can you calculate the value of the gas constant? Another one is you must remember this value because this is the constant value and you have to use in several numericals or the some sort of the calculations. So let's have a look on the what is the deviation of the real gas from the ideal gas. So there are the two conditions which are given over here, and again this is the again actually here in a similar way I am going to use this equation to verify that either your gas is the ideal or it is the non-ideal. So in the previous individual law, we have used the Boyle's, Charles, and the Avogadro law, and here we are going to use the state. This is the equation, and this is called the ideal gas equation. And just rearranging this one, I am going to divide PV divided by N. That means here this factor will be equal to this factor. If the value of this is 2, that means the value of over here will be 2. If 2 divided by 2, that will give you the value of the 1. So this is given over here, PV divided by NRT. N is also 1. So when you PV is equal to RT, actually this is called the compressibility factor, and Z, the ratio between pressure and volume divided by gas constant and temperature, is equal to Z, and Z is called the compressibility factor. That is the extent to which a gas deviates from the ideal behavior. So actually we are using this equation to differentiate between the ideal gas or the real gas. So let's have a look what is happening over here. Again, when the gas is the ideal, so this is the ratio between the four variable PV divided by the RT. So the ratio will remain the constant. That means the value of the Z will be equal to the 1 again, because when you divide or with the same value, here if it is the 5 divided by 5, the value is 1. If it is 10 divided by 10, that the value would be 10. So that means whatever is the increase in the temperature or the pressure or the other variable, there is not change in the value of the Z, and it will remain the constant and the constant to the value of the 1. And when the gas is following this behavior, this is called the ideal gas. So first have a look on the first graph. What I have explained over here, I'm going to implement over here. This is the graph between PV is equal to RT, PV divided by RT with the increase in the pressure. So look at the first is this is the dotted line is shown over here. This is the ideal gas, and the value is pressure 1. So 1.0 is the value, and this is the value of the Z. So when you increase the pressure, look at the value. The value is not going to be changed. That means it will remain the constant. And if the gas is following this one behavior, this is called the ideal gas. In other way, If the gas is falling on the temperature, that means actually the ideal gas, when you increase the pressure, there is decrease in the volume. So again, you will compensate this one ratio. This is not going to change. This will remain the constant because according to the Boyle's law, pressure is inversely proportional to the volume. So the gas has to follow the ideal gas law, and the value of this Z will remain constant, which is 1, and this is the ideal gas. And look at some of the gases are mentioned over here. These are the four gases which are the real gases, not the ideal gases. So how they are going to deviate from the ideal gas? Look at the pressure. That means now if the Boyle's law is not going to be implemented over here, pressure is not or the volume is not inversely proportional to the pressure. That means this ratio will not be the constant throughout the pressure. When this is not the constant, actually you will not get the value of the Z will be equal to 1. So look at it is very close at the start when the pressure is small. So these lines are very close to the ideal gas line. So that means at low pressure, these gases are going to follow the behavior of the ideal gas. So this is at very low pressure. Okay. So when you increase the pressure from 0 to 200, 400, 600, 800, 1000, look at, let's suppose this is the hydrogen. Now the ideal behavior is going to be deviate significantly by increasing the pressure. So you can say that it is near to the ideal gas equation or the ideal gas, but it is being deviated significantly when you increase the pressure. So that means one explanation is, if you will not get the state line having the constant value of the Z, then the gases are the real gases. So this is the one explanation through this graph. Another one is, at the different variable temperature, if uh, the temperature have different variable of the pressure, if the pressure is small at the start, then these gases uh, are going to be less deviated from the ideal gas. That means they are very close to the ideal gas. So these real gases are very close to the ideal gas. So the third point is, at high pressure, they are significantly deviated from the ideal gas. Now look at the other variable. Same is written over here. So I am taking the example of the nitrogen. Nitrogen is this. This is the graph for the nitrogen. I have taken this graph. So now this is the same axis. PV is equal to divided by RT, PV divided by RT versus the pressure. So what is changed from this graph to this graph? I have taken only the nitrogen, but the nitrogen is treated with the different temperatures. So I am going to have the effect of the temperature on the deviation of the real gases from the ideal gases. Again, the value of this Z will remain the constant. This is the ideal gas. That means according to the Charles law, now this is the relationship between the, because the P will remain the constant, N is constant, and Charles law is the variation with the volume and the temperature. And when you increase the volume, or volume is proportion to the temperature, when you increase the temperature, there is the increase in the volume. So again, because these are proportional to each other, if this is going to increase from 2 to 4, this is also increased from 2 to 4. That means this is the ratio between these two will be the same, and the value for Z will be the 1, and this is the ideal gas equation. So what is happening? That means whether you increase the temperature from 200 to 500 to 1000, there is no change in this straight line. And when there is no change in this straight line, the z will remain the constant, having the value of 1. That means the gas is the ideal gas. In other case, it is not the ideal gas, it would be the real gas. So now look at here we are going to explain in a similar way. That means at low pressure, the real gases were close to the ideal gases. And now here we are going to look at the temperature, at what temperature the gases are near, or near to the real gases are near to the ideal gases. So these are the three temperature are given over here. So look at when the temperature was small, there is the great or the more deviation from the ideal gas. So when you increase the temperature, now the deviation will become less. So deviation is from ideal gas to the this point, or you can take any of the point. Okay, so I'm just taking as a reference over here. So when you further increase the temperature, again there is the less deviation. So this behavior is the same as given over here. So when the pressure is small, again look at the deviation is the at the start, the deviation is small. That means at low pressure the gas is very close to the ideal gas, as explained over here. Now at higher temperature, look at the graph as compared to this. At high temperature, the gas is close to the ideal gas as compared to the low temperature. And if you further decrease the temperature, there will be more deviation from the ideal gas. So these are the second factor, what we have discussed over here, the deviation from the ideal gas at higher pressure and the low temperature. So now I'm going to conclude over here. So condition for the ideal or the real gases at low pressure and high temperature, real gases show nearly ideal behavior, and the ideal gas equation is followed. So these condition I have explained before. At low pressure and high temperature, so deviation is less. That means look at the over here, this was the same graph for the nitrogen. And uh, again there is a small deviation low pressure, but you further if you increase the temperature, this is line is more followed up to this temperature, up to this pressure. And that means now at high temperature this deviation is less as compared to the low temperature, which is starting from over here. So this is the behavior uh, of the real gases with the ideal gases. So if it is reverse, that means at low temperature and high pressure, opposite to the first uh, point, then real gases deviate significantly from the ideal gas behavior, and ideal gas equation is no longer valid. So I'm talking over here, if the pressure is high and the temperature is small, there is the more deviation. And when it is more deviation, that means this ideal gas is not going to be valid, and we need another gas equation and for the real gases, which I will explain in the next lecture. So the third point is noble gases act like the ideal gases because they do not participate in chemical reactions, and that's why these are the noble gases. And one of the example is the helium is a particular act like an ideal gas because it is having a atom so small as compared to the rest of the noble gases. So these are the condition for the ideal or the real gases. This is the exercise one, how to convert or how to get the useful results by using the ideal gas equation. So this is very simple calculation. So don't be worried about the exercise over here, because this is very fruitful exercise. You can use the ideal gas equation and to get the very important information. So the question is over here is how many moles of air are in lungs of an average adult with a lung capacity of 3.8 liter. If it is having 3.8 liter capacity, so how many number of moles of the air are present in the lungs? Assume that the person is at 1 atmosphere pressure and has a normal body temperature, and normal body temperature is 37 degrees Celsius. So that means this is a strategy which is explained over here. The this problem asks for the values of n, because you have to calculate the number of moles, and when p, v, and t are given, and these are given in the data, you have to put all these in this formula and to get the value of the number of moles. So pv is equal to nRT, n will be equal to pv divided by RT. The pressure is 1 atmosphere, volume is 3.8 liter as given in this exercise. R is having 0.082106 liter atmosphere per Kelvin per mole, and temperature is 37 degrees centigrade. To convert into the Kelvin, it would be 310 Kelvin. Again, what important point over here is it is the value of the gas constant. I am using the 0.0821 liter atmosphere per Kelvin per mole, because the pressure and the volume is given in the liter. So you cannot use the other value, which is the 8.314 joules per Kelvin per mole. So this is not suitable here. Again, when you put the units along with, so these all units are going to be cancelled out, and what is left, this is the double divisions, it will be the number of the moles which is your requirement. So this will directly you can verify by the unit cancellation method over here. So value is 0.15 mole. So the lung of an average adult hold 0.15 mole of the air, and which is having the capacity of 3.8 liters. So look at this, is very important calculation you are getting out of this exercise. Exercise 2, it is also very important. You can label the unknown gas, and this is the question which is given over here: to identify the contents of an unlabeled cylinder of a gas. uh, and the sample was collected and found to have density of 5.380 gram per liter at 15 degrees centigrade, and the pressure is 736 of mercury. So what would be the molar mass of the gas? Actually, a unlabeled gas cylinder, how can you identify? If you know the molar mass of the gas, you can easily identify the gas which is being occupied in the cylinder. So what information it is given over here? This density is very important. That means you have the sample of this 1 liter containing 5.380 gram. So the weight is given, the volume is given, temperature is given, and the pressure is given. So what important over here is to get the molar mass. Molar mass is the uh, grams uh, per mole, and the weight is given. And the first you have to calculate the number of moles, and then we are dividing the mass by the number of moles to give the value of the to molar mass. So this is a strategy. Again, by using the same equation, PV is equal to nRT. First, you are going to calculate the number of moles. N will be equal to PV divided by RT. And now put the value of all the uh, values over here in this formula. The pressure is 736 of mercury. Again, you have to convert this of mercury to the atmosphere, because the unit of the gas constant are liter atmosphere per Kelvin per mole. So this is very important. If the volume is given in other unit, you have to convert into the liter. If the pressure is given in other unit, you have to first convert the pressure to the atmosphere. And in a similar way, if the temperature is given in the other unit, you have to convert the temperature into the Kelvin, and then you will get the value of the mole. So what is given over here? 736 mm of mercury. Again, by using unit cancellation method, 1 atmosphere will be equal to 760 mm of mercury, and this mm of mercury is going to be cancelled out. What is left? Atmosphere is left. So, and now we have done with the pressure, and this is the volume is 1 liter. This is the value of the gas constant, and this is the value of the temperature. Temperature is given over here is the 15 degrees centigrade, and you have to convert it to the Kelvin. Now Kelvin is Kelvin cancel out, liter is liter cancel out, atmosphere is cancel out. What is left? Number of moles are left. So the value is 0.0410 number of moles. Now you can convert this number of moles to the molar mass, and molar mass or the molecular mass is the gram per mole. So gram are given in the density 5.380 gram, and you have calculated the number of moles by using the ideal gas equation, and the value is equal to 131 gram per mole. So this is the actually the mass near to the xenon. That means in the cylinder it is having the xenon gas, and this conversion or this calculation is also very important, because by using the simple calculation you can identify the nature of the gas or the unlabeled gas which is filled in the cylinder by using the ideal gas equation. And over here in a similar way we have calculated the xenon. So this is all about our today lecture.